pronounce the name incorrectly. Zi-Kui Lu, is that right? So please, we are looking forward
to you. Thank you. All right. Let me share my screen.
Yes, please.
Okay. All right. First, I want to thank the organizer for giving me the opportunity to present our work here. It says SBA in my title, but I thought to make it a little bit broader beyond the SBA. But I really like the previous speaker just mentioned the challenge. It's our challenge too. So I'm from the material science engineering department. So we work on engineering materials. As you know, engineering materials are usually multi-component. So I take an example, 6-component system, but of course, usually materials are more than that. So we develop a very good database, everybody's happy and use it, right? However, suddenly you find that you need to change something. You get new data for the P element C. Then you see the problem is that you need to change C, all this one with the C's, all this with the C's, right? Just like exactly what he mentioned, you cannot do it because you don't have original data and you don't have all the pedagogies people used. Everything's gone, right? Students left, and so forth. It's very difficult. So a few years back, we decided maybe we should tackle this problem. So we thought maybe we should put this data together. Very close to the idea the previous speaker just mentioned. We probably should collect all the data we have. Don't trash them, but don't just stay in one computer and rather keep them everywhere. And then with the iterations, then we get new data, we just do all things together, right? Once again, so it's a kind of all the data stored and the process is automated. That's how we started. But of course, that's the end of now. But I want to go back to the beginning and why we do this one. So 2 years ago, I wrote a paper kind of summarize what we try to do. I call it ocean of data. The idea to call the ocean of data is really kind of evolving, right? Because it's not just static data there. The data has to change all the time. You get new data from the first principle calculations, then you do modeling, you get new data from machine learning. So when I finished this draft of the paper, I talked with our technical staff at Penn State, and she's in charge of communications. I said, can you draw a diagram for me so I really reflect the idea I have about this ecosystem? And then she came with a very nice diagram, and she said that's probably what you meant. Okay, so it means a lot of data. We call it data lakes. We have data streams. We have even some private data. But if we put all the data together, we develop a database. That's what we call a CAFA database. And then the database can be used for materials design, materials processing, and generate new data, right? So you come to a cycle and try to take all the data possible, available, and put them together to do design. So that's the idea we call the ocean of data. So then 2 years later, I said, oh, maybe I should review it a bit further. What did it really mean of this ocean of data concept? It's really that what's behind the bottom, right? Of course, as you can see that I do thermodynamics, which I believe thermodynamics is the base for everything. So it's really talk about the stability, metastability, instability, and about diffusivity, and all this stability coefficients and the mechanical properties too. So I try to put it in this kind of context that what you can do with it, with the energy. Now, go back to step about thermodynamics. I have one slide, like 2 slides about thermodynamics. And usually that when we learn from school, the people say, oh, thermodynamics for equilibrium. But is that really true? If you look at the first law, no, it doesn't say it has to be equilibrium, right? But however, if you look at another equation we usually see from a textbook, it is for equilibrium only. So what's the difference between these 2 equations? Is actually one term missing. What is that term is? It's called entropy production. Okay, if you put entropy production back into that equation, it actually for non-equilibrium system. The question is how do you define this quantity, right? What does the psi means here? Of course, we do not work with internal energy, we work with Gibbs energy. They just change the independent variables. What it means is that Gibbs energy is a function of temperature pressure composition, as we usually say, but it's also a function of internal degree of freedom. So the psi really means the internal state variables. Okay. I want to make a advertisement here. I'm going to have a talk. In 2 weeks. I title called Entropy, which will be in Duke University. Of course, it'll be virtual. And they talk about more details how the thermodynamics are kind of beyond the non-equilibrium, beyond equilibrium, and even more that a lot of properties can predict. I do want to show 2 slides on this one. So this is called derivatives between x and y. What's x and y is here. So x and y, there's a molar quantity of potentials. And we all know this one because this is the Maxwell relation. The matrix, this matrix is symmetric. So this is called the derivatives between x and y, which is the second derivatives of the energy. So now the important message I want to mention here is that this diagonal terms is all positive for stable system. However, it's off diagonal terms could be positive, negative, 0, or infinite. Okay, so that makes it very interesting. And to start, that's what friendly function is very important. And if you can do another derivative, which type of derivatives has been very little discussed, is between 2 potentials. And turned out it's even more interesting properties there. I did discuss it even more in that paper I had written last year. There's more papers come out about this derivatives here. So now you see the key thing is really to get the free energy, right? Get the Gibbs energy, not only as a function of temperature, pressure, and composition, but also the internal degree of freedom. Okay, to do that, I want to talk what is really this psi is about, internal degree of freedom. Of course, we know that, for example, why is a non-stable light structure, BCC copper? We know copper is FCC. However, BCC copper doesn't form together with iron. You can form BCC copper in iron matrix. So in that case, we need the BCC copper energy, but we know that we really cannot measure it, but we can calculate with DFT. And then you can talk about the difference between stable and the stable one and the non-stable one. In this case, actually, it's unstable, but you make it stable by strain, because this is one type of internal variable. And another one is the ordering, right? You have the long range ordering, like the sub-lattices. You can talk about the polarizations. You can talk about all defects. So all defects actually are kind of internal degree of freedom. If we can model them together, then we can actually predict the properties. Okay, so now I come to the modeling. So I introduced a model called cathode modeling, which is about individual phases. You talk about the Gibbs energy of a phase, with the temperature, pressure, composition, and internal degree of freedom. To do that one, you will need a data. Experiment data is not enough, because experiment data usually measure equilibrium. When systems are equilibrium, psi becomes a dependent variable, so it disappears from the equation. That's why we call it equilibrium thermodynamics. So in order to model this one, we have to get the data from the derivatives too. Okay, derivatives. So this is equilibrium. Actually, there was talk about NPDS the other day, Monday, about the database phase diagrams. That's what the data. Actually, we try to build up interface with the NPDS database. I try to get the phase bundle data, but we also need the derivatives. And you do this from, as I showed on the first slide, you start from the pure element, the binary return, and multi-component system. You can buy commercial databases like over 20 elements databases for your material design and material simulations. So as soon as I get the database, you can do material design, the equilibrium calculation for the first one. And then you can also do driving forces, that's for your phase transformation. And then you can also do derivatives. I mentioned that 2 tables for all kinds of derivatives. Okay, so I do want to get another slide about cathode community. Cathode it's a small group, a few hundred people. It's a modest Gibbs energy, and it has a conference, annual conference. If you go to www.cathode.org, it has been going on since 1973. And it is a private foundation, which is financial back for the society. It provides scholarships and awards. We have a journal since 1977. And so the commercial ones, if you go to major companies in the world, and the Fortune 500 companies, most of them probably use the cathode databases for the material simulations. They probably even either use ThermoCAD, FactSage, or PanDat, or GMAT Pro, or MetaCAD for their materials calculations. They usually do is that do some calculation first, then do some experiments, then go back to calculation, experiments. That's kind of help them to do that. Of course, if you have heard a talk by Greg Olson and Questec and the SpaceX, they use ThermoCAD and the PanDat as kind of tools too. We also have open source. open source code, the PyCAFAT, OpenCAFAT, and some chemical, and the PyCAFAT is this code I'm going to have a few slides talking about today. I do mention that CAFAT is supporting the ICME and MGI. If you read this book, in 2008, by the ICME, that it actually stated that CAFAT software, and I should add here CAFAT software and databases, okay? And because these two go together, it's really the generic tool for ICME. And if you know if you heard about the Material Genome Initiative in 2011, and the two papers, which many papers, and the Gregos and Charlie Kuhlman, and one paper, I wrote another paper on top of the material genome and how CAFAT is supporting that. Okay, so how do we do CAFAT model? So we take, I mentioned it started in the 1970s. So you take experiment data, you do some intelligent estimation, you do the model, you develop database. That's how it happened, and a lot of databases were developed and used by industry since the 1970s. And now we get first principle calculations. We get a lot of database now. We get a Matrix project, Airflow, and OQMD, and so forth, and discussed in the last 2 days. And we know first principles, most of them 0 Kelvin. So you have to put the finite temperature, get statistical mechanics, so you get a finite temperature there. And we started this one around the year 2000, where it came to Penn State, and we found it very, very powerful because it really made the database better. But the problem I just mentioned at the beginning is that now we have new data. We have a 20 component database. What are we going to do, right? So it's very difficult to change it. So we realized these problems, we decided to develop new tools for it. So we developed tools for high throughput and uncertainty quantification. So we wrote a book to discuss the philosophies, fundamentals there. And it's all open source we have. It's on GitHub, got a Faces Research Lab. It's our group. And we do 3 types of tools, so to speak. Data generation. We do machine learning. We build up I have one slide to show each tool. We do DFT-TK, which is based on DFT calculation of free energy. And then we do data processing, basically develop databases. And we particularly did PyCAFAT is that you can do your model. You can do your own model. For example, I think the previous speaker talking about the new potential, for example, right? New potential comes up. New models come up. You can use same data to remodel it. Yeah, so you can take different models. And then this is the analysis, evaluation parameters, then do uncertainty quantification on that. And we also do the trainings. We formed a nonprofit foundation called Materials Genome Foundation. And we have had a few years, but last year we had an online one because of COVID. So we have our recordings on YouTube. All right, so the data ecosystem, what do I really mean by data ecosystem? I mentioned this so far. So we get a lot of data from theoretical prediction, machine learning, DFT, and also we're doing the mechanical properties too, and experiment data. So we call those data proto data. These are data points, okay? And then we use the PyCAFAT aspect to develop databases. And for the databases, we can do design and manufacturing, and to service, you get new data. So new data go into the proto database again, and then you refine your database. And then you can do recycle too. You can recycle new data, right? So for the data, the idea is that this is going to be recycled around all the time. Now, I want to just show one slide about DFTK. As you see, as you heard a few days in the last 2 days, the PyMagic Fireworks, the custodian OPTIMADE has really high throughput tools, most of them 0 Kelvin. So we build on top of those tools and they do finite temperature for any configurations or structures. Again, as is open source, www.dftk.org, you can download and give comments there. And then the machine learning, it's also an open code. So the idea is that we follow what the Chris Watkins group and takes the OQMD data to train the different models, and then we can develop we can different models for different purposes. And of course, you can do the error estimation. But more important, you can also do the transfer learning. I think also a few people spoke about it. Transfer learning is very important because you have data beyond the data you have in the OQMD. So how can you refine your code machine learning models? And then we will put all together. We start we're going to go one step further. Because if you, after you get a machine learning model, you find that one of the most time-consuming step is actually to calculate all the descriptors for the structure you give. Okay, and in my slide, the first slide showed Adam Krzyzewski. Krzyzewski is one of our third-year grad students, and he developed this machine learning on this code, and it was presented at the MRS Spring meeting just a few months ago. And it's basically that we want to calculate the descriptors for any structure we have. That means all structure we have, the descriptors are calculated already. So when you come to a new structure, which is very close to the ones in the database, they take very little time to calculate the data. So we want to make this one be available. And so it's actually, it's very important that it's decentralized. It's going to calculate on all different virtual machines. And we hope to make it open public in the summer. Adam promised to finish in June. We'll hope it's get that done too by June or in the summertime. Okay, now comes SP. Now we get all the data, right? We need to develop a database for multi-component system. So we have two steps to do that. The first step is almost exclusively on DFT data, free energy, with stable and non-stable structures, configurations. Okay, and because we have so much data, right, from the DFT, so we have to be sure that we don't overfit it. So we get optimal combination of the model fitness and the complexity. So you can of course fit as good as you want, then your model is not a very good extrapolation. But if you can balance it, then good fitting and good machine, good extrapolability. And then, it's very important to realize that DFT data has a large error bar. Okay, if you use this data to calculate phase transformation or phase boundary, it could be hundreds of degrees off. Okay, so it's not useful it's far away from experiment. So another data is the phase boundary data, and what the MPDS, that's phase boundary data, right? So then you can refine the model parameters. It's based on parameter estimation method. It's a Markov chain Monte Carlo to refine the parameters. This refining process at the same time can generate uncertainty for the parameters when you have input data uncertainty there. So now every time we get new data, we can remodel it, right? Because you can all the files, they input the data for the modeling is saved there. It's JSON format, XML for JSON, so you can reuse them all the time. Okay, to do that, we'll have to build our own minimizer. So PyCap is our own minimizer. And the very important thing is that you can take your own model, okay? So you can custom models. And you know, calculate non-equilibrium state. You can specify your state. You can do the calculation. Of course, it knows the equilibrium calculation, that's minimization. And this is so well designed. My student, he left our group, then went to NASA and continued to develop it. And now, 2 years ago, he put us a competition and actually got second place. That's the software in 2019, NASA-wide. Okay, so what is the end of story we have? End story is that we got a Kafka database, we got the machine learning, the MPDD is here, and we are going to develop a new model. As I think I really like what the previous speaker mentioned. Physics-based model is very important. Okay, it's particularly important, that one. Then we'll hope to do inverse design. Then we'll get new experiments and models and first principle calculations, feed it back to the machine, ocean of data, and then to the modeling. We're also doing the natural language processing, get the literal data into our database. And of course, we hope a user can input that one too. And then we are in the process of developing an API. So OPTIMADE, I think it's a great idea. When I heard this group, I was so fascinated. I think that's a fantastic idea to put it together. So we are going to also develop API, and with the standard you guys develop it. With that one, I want to thank you for your attention.
Great, thank you very much for this wonderful talk. We have probably time for